On October 2nd, a blazing streak zipped through the Martian atmosphere at an astonishing speed. An amateur sky photographer called Stephen Burns spotted it while sifting through unprocessed shots from NASA's Perseverance rover. He pieced together a sped-up sequence from 9 minutes of footage, squeezed it down, and sure enough, the thing was darting along at 60 kilometers, bucking the usual drift of the stars. That's when things turned truly bizarre. Other enthusiasts jumped in to scrutinize the same photos, insisting they detected several items, not merely a single one. In the October 3rd footage, there were various swift oddities, along with an enigmatic green burst that defies explanation. NASA had planned this particular viewing session. A fleet of Mars satellites was set to snag the sharpest close-ups yet of an interstellar visitor. The Advanced Imager offering 30-kilometer detail, the Mars Express Orbiter, the ExoMars Trace Gas Orbiter, all trained on 3I Atlas right during its October 3rd pass by the Red Planet. Then, radio silence. No released photos, no shared info, zilch. At the same time, Harvard's Avi Loeb dropped a paper that's rattling the whole astronomy world. This 3I Atlas could be the origin of the legendary 1977 WOW signal. The likelihood that's pure chance, just 0. 6. Yet the WOW link is only the start, since 3I Atlas shatters every known pattern for comet activity. It's forging high-quality nickel compounds right in the void. Its trail veers off in the incorrect path. It glows green against all expectations. And its path lines up so precisely with Earth that the probabilities are off the charts. Folks are dubbing it the biggest interstellar find to date. Some label it outright implausible. Avi Loeb suggests it might even be engineered. For now, it's tucked behind the sun, out of sight, edging toward its nearest brush with our star. What unfolds when it reemerges? Before we plunge further, if this hooks you, smash that like and subscribe to catch the updates. Drop in the comments where you're tuning in from, the local time, and if you believe it's a lone entity or a bunch. To boost this group, spread the word on X, Facebook, Reddit, or via chat apps. Thanks for the constant support. Chapter 1. Hold on, multiple entities. Rewind to October 2nd. Stephen Burns wasn't hunting for the unusual. He was just handling the open-access raw files from the Perseverance rover that NASA shares freely. The vehicle had been tasked with scanning the evening heavens in a set time frame. That slot when 3I Atlas was forecast to swing nearest to Mars. Nearest, in this case, means a hefty 29 million kilometer apart. Burns compiled 9 minutes of back-to-back snaps into a quick clip. In sky imaging, this method uncovers shifts that vanish in a static shot. The stars trail across due to Mars spinning. But this stood apart. An element sliced through that flow at an illogical slant for any distant star. The velocity tipped it off first. Clocking 60 kilometers, 3I Atlas outpaces almost every body in our system. To put it in perspective, Earth circles the Sun at roughly 30 kilometers. The Parker Solar Probe, our quickest probe, hits 192 kilometers, but solely near solar perihelion. 3I Atlas holds that furious clip the whole way. Burns shared his clip on the web. Soon, fellow hobbyist stargazers launched their probes. That's when a user named Nachtaf German for Night Monkey dropped a bombshell that echoed across the watcher circles. In the October 3rd shots, Nachtaf noted, "You can spot several comets, not a solo piece, but multiples." Another observer, Alexander Fum, flagged a different detail. "What's that green highlighted flash at second ERU 3? Rewind and pour over Burns's clip one frame at a time. At that precise 3-second point, a subtle emerald glow emerges briefly. It's no glitch from the camera, nor a streak from a cosmic ray that would show up as just one glaring dot. Instead, this is a soft, spread-out radiance that's pinpointed yet unmistakable. In the vacuum of space, green illumination arises from particular sources. Down here on our planet, we link it to the northern lights, flames from burning copper, or glowing life forms like fireflies. Up there, though, such emissions usually stem from oxygen or a compound known as dicarbon, essentially two carbon atoms linked. Occasionally, comets take on a greenish tint when sunlight energizes the dicarbon in their surrounding clouds. But the issue here is clear. Detailed spectral scans of 3I Atlas taken by the Very Large Telescope, revealed almost no trace of dicarbon at all. The body is classified by experts as carbon poor. It ought not to emit any green light whatsoever. Still, shots from Earth-based observatories in the first days of September distinctly captured a greenish tint forming near the intruder. That fleeting green burst in the Mars photos, assuming it's genuine, deepens the enigma even further. As for the hints of extra bodies, this is where we venture into guesswork. Yet this pondering comes from folks equipped with scopes and editing tools, not wild fabricators. Once you steady the starry backdrop in Burns's video clip, factor in Mars's spin and the lead object's path, you spot at least one or two extra bright specks traveling at varying speeds. Might they be flaws in the footage? Sure thing. Could they simply be distant rocks crossing the view by chance? It's feasible. Or perhaps they're distinct chunks or tiny escorts trailing 3I Atlas. That's the puzzle no one can solve just yet, since NASA hasn't shared the raw files. The Mars Reconnaissance Orbiter's HiRISE instrument scanned 3I Atlas on October 2nd from 1 to 4 a.m., local Martian time. Meanwhile, ESA's Trace Gas Orbiter and Mars Express both recorded data the following day, October 3rd. These weren't offhand pics, they formed a deliberate joint effort to collect the sharpest details ever on an extrasolar visitor. HiRISE, the high-res imaging setup, can pick out surface details as fine as 30 centimeters from its orbital perch above Mars. Aimed at something 29 million kilometers distant, it would still deliver roughly 30 kilometers pixel. So, with 3I Atlas's core estimated at 5 kilometers wide lately, it should show as a vivid clump of pixels in those high-rise shots. Even better, the tool could tell a solid, tight core apart from a broken-up or multi-part form. If fragments exist, if a sidekick body lurks, or if the makeup is odd in any way, HiRISE would catch it. So why the hold-up on those visuals? NASA's brief update simply noted that the orbiters completed their scans successfully, with data now under review. More info to follow as they dig in. But that message dropped over 24 hours back. In astroimaging circles, that's ample time to at least skim unprocessed frames. While U.S. agencies grapple with bureaucratic snags delaying science releases, ESA runs on its own. They face no such roadblocks, and yet their pics remain unseen too. This hush seems intentional, and when pros clam up, hobbyists fill the airwaves. What stands firm is this: the Perseverance rover did snag footage. Various independent reviewers poring over the same open raw feeds have flagged oddities. Those shapes or clusters traveled at speeds matching 3I Atlas. And that baffling green spark lingers unexplained. The unknowns persist. Are those seeming extra forms authentic, distinct from the primary comet, and what did NASA and ESA's superior gear actually reveal? The October 3rd flyby marked the nearest encounter any probe has achieved with an active interstellar visitor. This presented our opportunity to unravel the true nature of 3I Atlas, to examine its composition in detail, and to assess whether it acts like a typical comet or something far more unusual. Meanwhile, as anticipation builds for revelations, the entity presses on with its path. Currently, it's nearing the Sun, venturing further into the heart of the solar system, where ground telescopes on Earth struggle to track it amid the overwhelming solar brightness. Come late October, it will slip behind the Sun from our viewpoint, vanishing entirely from sight. When it reappears in November or December, it could either validate all the conventional theories or reveal behaviors that no comet exhibits. Yet, prior to its disappearance, it's essential to examine the true objectives of the Mars observations and why this prolonged quietude carries greater significance than it might seem. Chapter 2. The Mars Blackout. Space organizations follow a predictable rhythm in managing delicate data captures. Routine detections surface swiftly, with raw visuals flooding open archives, announcements prepared, and experts sharing updates online. But when anomalies emerge, the hush lingers longer. Officials attribute holdups to data handling workflows and adjustment needs. Mars satellites don't relay visuals instantly. They record them internally before sending bursts to Earth in planned slots. Afterward, the information undergoes several refinement steps: shape adjustments, light balancing, interference removal. Standard planetary scans wrap up in 6 to 12 hours, while tracking a swift body amid the stars might double that time frame. Yet here we are, exceeding 48 hours since the October 3rd captures. Another element lurks unspoken in public updates, though it circulates among scientists relying on NASA feeds for their research. Funding limits and operational hurdles have clogged release mechanisms, not an outright halt, but the sort of red tape that slows everyday operations into sluggish affairs. Teams on shortened schedules, task priorities shifted, approval sequences extended, ESA functions under separate governance, but their Mars Express and ExoMars Trace Gas Orbiter visuals remain absent too. This points to either a joint choice to hold back initial findings pending thorough review or shared technical hurdles both groups are tackling in tandem. So what could prove demanding enough to trigger such a stall? Reflect on the capabilities of these tools. The CASIS instrument on the Trace Gas Orbiter can discern details as fine as roughly 4.5 meters per pixel when aimed at Mars, even from 29 million kilometers distant at a remote target. That sharpness diminishes markedly, yet the device's acuity holds strong. Built to spot faint hue shifts in Martian terrain, it would register if 3I Atlas was releasing diverse ices, displaying varied makeup in its envelope, or featuring unique structural zones. Mars Express deploys the high-resolution stereo camera, which, contrary to its label, excels at mapping 3D landscapes. For a far-off comet, its depth sensing is secondary to capturing scenes in various light spectra at once. This setup allows separation of particles, frozen water, CO2 frost, and assorted rocks by their light reflection signatures. Then consider the Mars Reconnaissance Orbiter's HiRISE, which we've touched on, but one aspect we haven't explored. HiRISE goes beyond snapshots. It gathers info in 3 spectral ranges: blue, green, red, plus near-infrared. Directed toward a comet, different wavelengths highlight various elements of the comet's makeup and behavior. Blue-green illumination engages with the gases surrounding the nucleus. Meanwhile, red and near-infrared wavelengths cut through sparse dust layers, exposing underlying formations. Should the comet be ejecting streams of substance from particular spots on its core, should those streams vary in makeup, or should the illumination differ over the body in patterns indicating an uneven exterior, the HiRISE instrument would capture every detail. Now, regarding delicate imagery, it occasionally reveals elements that demand expert review prior to sharing, not due to any cover-up, but simply because early findings might be misconstrued absent the right background. If HiRISE spotted anything out of the ordinary, the team behind the mission would seek to eliminate possibilities like equipment glitches, cosmic ray interference, or data handling mistakes before releasing the information. Yet, as we anticipate updates from formal outlets, enter Simeon Schmaus. This astrophotographer excels at refining unprocessed data from celestial bodies. Within enthusiast circles, he's renowned for pulling clear signals from cluttered visuals, steadying unsteady footage, and highlighting faint details overlooked in first-pass treatments. On October 1st, just a day prior to Stephen Burns' October 2nd time-lapse, Perseverance snapped a sequence of nighttime celestial shots. These landed in NASA's raw image archive shortly after transmission back to our planet, as is standard for the rover's output. Schmaus grabbed them promptly, ran his custom enhancements, and asserted he'd spotted an initial view of 3I Atlas within the shots. No one has corroborated this assertion yet. At such a range and position, the entity would appear incredibly dim, yet if valid, it implies the comet became visible ahead of the primary viewing period. Even more captivating, Schmaus observed that the movement he identified strayed slightly from the forecasted path. It was near, yet off by a small margin. He shared his observations online, noting that further examination was essential, though the initial outcomes proved fascinating. Afterward, mirroring the official entities, he fell silent. Is he continuing his review, holding back on a discovery until verified for public talk, or perhaps advised to pause? That's unclear. What remains certain is the divide. A divide separating expected transparent releases from the current reality. a divide between planned viewings and the information accessible for scrutiny, a divide brimming with hobbyist breakthroughs, baffling green bursts, and assertions of several entities that officials neither affirm nor refute. Perseverance presses on with its ground operations. Its optics stay operational. Its feeds keep flowing into the open repository. However, the key shots from those vital evenings, the most significant ones, undergo quiet evaluation. Come October 29th, 3 Atlas will hit perihelion, drawing nearest to the Sun. From our vantage, it'll then sit fully obscured by Sol, out of sight for both terrestrial scopes and orbital platforms. The chance to observe is narrowing. No matter what NASA and ESA detected, what Shmooey uncovered, or what's unfolding amid the checks and data flows, time is ticking. For if this body harbors anomalies, if those varied light sources exist, if the green flash signals import, we must learn before it vanishes amid the Sun's brilliance. Should answers evade us, we'll linger until November, when the comet reappears opposite, possibly altered from its solar brush, possibly exhibiting behaviors beyond typical icy wanderers. Yet, timing holds further significance. As attention is centered on potential revelations from the Martian vantage, Avi Lobo has peered rearward, following 3I Atlas's route, extending beyond merely our solar system, yet spanning across time. His discovery links this item directly to one of the greatest unsolved transmissions in astronomical records. Chapter 3. The Explosive Revelation of the WOW Signal. On August 15, 1977, Ohio State University's Big Ear Radio Telescope was performing its standard scan of the heavens, hunting for transmissions that could hint at advanced societies elsewhere in the cosmos. The instrument ran on autopilot, sweeping through slim slices of radio waves and recording strength levels on endless rolls of paper. 3 days afterward, astronomer Jerry Ayen examined the records and spotted an anomaly that prompted him to reach for a red marker. A burst had emerged, a potent focus spike enduring precisely 72 seconds. Its strength soared well beyond the usual static, so Ayen highlighted the code and scribbled a single term beside it. Wow. The emission originated from the Sagittarius region, close to the star cluster M55. It registered at 1420 MHz, right in the safeguarded zone for radio astronomy. No earthly broadcasts are permitted there. The emission's width was slim, under 10 kHz, matching the profile of a manufactured broadcaster more than a cosmic phenomenon. The Big Ear picked it up just once. Subsequent scans turned up empty. For almost 5 decades, the WOW signal has lingered as one of the field's biggest enigmas, right up until Aviv ran the numbers on 3I Atlas's location that day. By reversing from its present course and speed, Loeb mapped its journey backward through the void. Back in August 1977, 3I Atlas sat roughly 600 astronomical units away from our planet. That's 600 times the Earth-Sun span, deep in the solar system's fringes, though still shy of full interstellar territory. The WOW signal arose from sky positions at right ascension 19 hours 25 minutes in declination minus 27 degrees, aiming into Sagittarius. Loeb figured 3I Atlas's spot on August 15, 1977, right ascension 19 hours 21 minutes, declination minus 19 degrees 4 minutes, a gap of 4 minutes in right ascension and 8 degrees in declination. In skywatching lingo, that's strikingly near. The odds of 2 arbitrary sightlines converging within 9 degrees? Around 0. 6. Still, mere overlap doesn't confirm a link. Loeb dug deeper. Should 3I Atlas have sent the WOW signal, what sort of output would its emitter demand? Big Ear captured intensities from 30 to 30 Janskys. A Jansky gauges radio brightness. By contrast, top sky radio emitters like the Sun or Jupiter hit hundreds to thousands of Janskys at certain wavelengths. From 600 astronomical units out to achieve that detected power, the sender would need to beam anywhere from 0.5 to 2 gigawatts. That's akin to a standard Earth-based nuclear plant's capacity, far from outlandish and hardly cutting-edge for a society mastering star-hopping journeys, yet it fits neatly as the energy profile for a far-flung scout relaying messages over immense gaps. One more intriguing aspect. The WOW signal displayed a subtle frequency drift. It clocked in at 1420, 4:05 p.m., roughly 10 kHz above the neutral hydrogen marker. That's a blue shift, signaling the origin was approaching our world. 3I Atlas approaches the Sun at about 60 kilometers. Factoring in Earth's orbit and setup that August, the approach speed would induce such a blue shift. Loeb computed the projected offset. It aligns closely with the reading, if not spot on. Any mismatch might stem from imprecise path or speed details, or from the beam aimed in a targeted beam rather than omnidirectional transmission. This is where things turn fascinating from a tactical perspective. If an intelligent entity aimed to reveal its existence, sending out signals close to the hydrogen line would be a smart choice. Hydrogen ranks as the universe's most plentiful element. The 21 centimeter hydrogen line holds such a central role in radio astronomy that any society advanced enough for radio tech would keep an eye on it. It's essentially the Milky Way's universal invitation frequency. The WOW signal persisted for 72 seconds due to the Big Ear telescope's design. It featured 2 feed horns positioned apart in the sky, each tuning into neighboring areas as Earth's spin carried them over the area of interest. Every horn covered a 36-second interval. The signal showed up in the horns one after the other, resulting in the full 72-second capture. That suggests the origin kept emitting steadily, or at minimum, throughout the span that Big Ear tracked it. Not some fleeting burst, but an ongoing emission. Should 3 Atlas have been the culprit, it sparks urgent inquiries right away. Could it have been a marker signaling its location to listeners? Perhaps a positioning beacon for another vessel? Might it have been a bit at contact, carrying data too complex for us to unravel? Or simply a fluke of the cosmos, where an extrasolar comet lined up just right with an undiscovered natural radio emitter? The issue lies in our absence of radio telescope records for 3 Atlas. None from August 1977 for sure, and none today. No facility has aimed its radio antennas at this thing. Efforts have centered on visual exams, spectral analysis, and photos. The inquiries revolve around makeup and form, not on potential transmissions. Lowe insists that must shift without delay. The body is nearing its closest solar approach. It's drawing nearer to the Sun, implying greater heat, increased dynamism, and extra power if any engineered setup is at play. If it sent out a signal once from 600 astronomical units away, if it's built to signal at key stages of its path, now's the moment. Facilities like the Very Large Array in New Mexico, the Arecibo replacement sites, and the expansive setups in China and Australia could scan 3 Atlas over a range of bands, beyond just the hydrogen line, but throughout the areas where crafted signals could emerge. The process would be simple. Aim. Tune in. Measure against the noise, hunt for tight band emissions, any rhythmic variations or repeating forms that nature doesn't yield. If empty, no harm done. It just takes a handful of hours on the scopes to dismiss the idea. But if something turns up, if 3 Atlas is putting out radio waves, even weak, even sporadic, that reshapes our entire view of this visitor. After all, a comet doesn't transmit. A lump of frozen debris and stone, no matter its stellar origin, doesn't craft radio at targeted wavelengths. Natural sky phenomena do release radio waves, yet they're wide-ranging and disordered, without the deliberate patterns that hint at purpose. The WOW signal showed pattern. It featured a slim bandwidth, it popped up at a significant wavelength, and if Avi Loeb's take on the match holds true, if that slim 6-to-6 overlap signals real connection. Then, out in the solar system's fringes 4 decades and 8 years back, an entity beamed a strong enough pulse for detection. That entity is now hurtling by Mars, concealed from sight by the Sun, pulling off feats beyond a comet's norm. The real wonder isn't if we ought to tune in. It's why we haven't started yet. Chapter 4. It's forging industrial metals up there. As comets near the Sun, they start losing bits from their outer layers. Ice turns straight to vapor through sublimation. Dust grains rise free. Locked-in gases break loose. And now and then, should the comet venture. When temperatures rise sufficiently, tiny quantities of metals evaporate from the dust particles trapped within the ice. Nickel and iron emerge jointly in these ejected gas streams, consistently paired due to their shared origins in stellar formation, their coexistence in meteorite compositions, and their comparable sublimation points. The proportion fluctuates modestly across different comets, yet it adheres to a consistent trend. For each nickel atom identified, roughly 10 iron atoms are anticipated. The earlier interstellar visitor, 2I Borisov, conformed precisely to this pattern. Comets from our solar system do as well. Virtually every frozen object we've examined exhibiting metal emissions obeys this rule, with the sole exception of 3I Atlas. The European Southern Observatory's Very Large Telescope in Chile has been monitoring this body using its ultraviolet and visual Echelle spectrograph, a tool engineered to dissect light into its spectral components with exceptional accuracy. From August through September, scientists gathered spectral readings over 6 intervals while the comet approached from 3.14 astronomical units to 2.14 astronomical units from the Sun. In each session, nickel spectral lines shone vividly and distinctly in the data. Iron lines only surfaced once the comet drew nearer than 2.64 astronomical units. Prior to that point, nickel emissions occurred solo. Beyond it, nickel persisted alongside iron, but the proportions deviated wildly from those in other comets. The nickel-to-iron ratio registered magnitudes above solar elemental abundances, exceeding standard cometary values and surpassing yields from typical geological activity. The emission volume amplified the anomaly. 3I Atlas was expelling nickel vapor at around 5 grams per second during initial sightings. As it neared the Sun and heated further, this output surged markedly. 5 grams per second might seem negligible at first glance, but its implications are profound. That's equivalent to 430 kilograms daily or over 3 tons weekly from a body predominantly composed of water, ice, and rock. At 2.8 astronomical units, where most of this activity was detected, the surface heat remains far too modest to volatilize silicate minerals or metallic inclusions harboring nickel and iron. The comet would require at least double the proximity to the Sun for routine evaporation of such durable substances. An alternative process must be at play. The study group outlined multiple hypotheses. Nickel might reside in a readily liberated state. For instance, nickel tetracarbonyl, a volatile molecule, could decompose via ultraviolet radiation, freeing individual nickel atoms into the surrounding haze. However, synthesizing nickel tetracarbonyl demands precise chemical reactions under defined circumstances, pathways rarely encountered in nature. Here on Earth, we manufacture it through industrial means as a key step in refining nickel from ores. The process involves heating crude nickel with carbon monoxide under controlled heat and pressure to generate the gaseous nickel carbonyl, which is then thermally broken down to yield refined nickel. The profile of 3I Atlas emitting nickel-absent matching iron echoes the byproduct of this refining technique. The team also considered other options. Nickel could be incorporated into organic molecules or present as nanoscale particles that react uniquely to solar warmth compared to larger metal chunks. Alternatively, photon-stimulated desorption, where sunlight directly ejects atoms from the surface, might favor nickel release. These represent feasible natural explanations, intricate and condition-specific, yet conceivable. Natural processes, though, typically produce detectable traces. They rely on foundational ingredients and hinge on the object's evolutionary background, its interstellar travels, and the radiation it has endured. 3I Atlas probably originated in the Milky Way's thick disk, an area populated by ancient metal-poor stars. Simulations indicate it endured 4 to 7 billion years, voyaging across the vast emptiness between stars prior to arriving in our solar system. It would have encountered cosmic radiation, ambient cosmic rays, and impacts from interstellar particles and gases. Might such encounters have sparked unusual surface reactions capable of accounting for the nickel release? Perhaps the comet picked up substances along the way that, now warmed by solar energy, emit metals in atypical proportions. One would anticipate that comets originating near various stars display distinct chemical profiles. Protostellar disks differ in makeup across the cosmos. The blend of elements, the balance between easily vaporized and heat-resistant substances, the makeup of carbon-based compounds, all these factors shift depending on the location and era of a star system's birth. Yet the principles of physics remain constant. Nickel and iron continue to emerge side by side in stellar explosions. They persist in clumping together within forming disks around young stars. They evaporate at comparable heat levels. To force them apart and unleash them in starkly uneven amounts demands defying core chemical bonds. Except if the nickel isn't vaporizing from frozen water and minerals, if it's emerging via mechanisms we rarely link to comets. Avi Loeb has logically noted that the findings align with patterns seen in manufactured nickel sources, not implying the comet operates as a manufacturing site, but suggesting that should it be an engineered artifact featuring nickel-heavy parts or a layer of nickel-laden buildup from its cosmic trek, the sun's warmth might erode that layer. The absence of iron would merely mirror the makeup of the eroding substance. The rebuttal is direct. Why would a sophisticated society construct an object from stuff that erodes so readily? When crafting a probe for interstellar endurance spanning eons, you avoid substances that begin to gasify upon approaching a sun. Unless the evaporation is deliberate, unless expelling a cloud of matter fulfills a function like thermal regulation, shedding weight to tweak its path, broadcasting signals, or forming a detectable beacon visible from afar. Or unless the gathered layer from the voyage wasn't intended in the initial blueprint. After all, the void between stars holds traces of matter. Traveling at 60 kilometers, even sparse clouds of gas and grains strike with considerable force. Across millions of years, a vessel would gather outer deposits akin to those on a comet. Should those deposits prove abundant in specific elements, influenced by the galactic zones it crossed, odd elemental mixes could appear. Observations from the Very Large Telescope offer no confirmation of these ideas. They merely confirm that 3I acts in puzzling ways. The iron-free nickel, the intense emission levels, the sequence of when various gases emerge, none mesh neatly with standard comet theories, and nickel represents only part of the puzzle. Meanwhile, as the VLT recorded metallic outflows, the Hubble Space Telescope snapped photos exposing an even deeper issue, one that questions the essence of cometary nature itself. Chapter 5. The Anti-Tail Anomaly. The tails of comets stretch opposite the sun's direction. This ranks among the basics of comet lore, not due to trailing the nucleus's path, but from the shove of sunlight and charged solar particles. Light particles possess push. As countless photons bombard specks of dust and charged vapors each second, they impart that push away from the sun, forming the signature streamer that flows ever outward from our star. This orientation lies at the heart of how comets act, so much so that observers can pinpoint the sun's position simply by noting the tail's angle. On July 21st, Hubble secured the sharpest view to date of 3I Atlas. The comet lay at 211 millions of miles away from Earth. The object is still heading toward its October closest approach to the sun. The captured image reveals a hazy radiance in front of it, directed toward the sun. This radiance stretches out about 10 times its width, shaping a droplet or stream-like form. In the rear, where a tail would normally trail, there's emptiness. No vivid spray, no prolonged dust path, just a subtle fade of diffused light into the surrounding void. That radiance is an anti-tail. Such features aren't entirely rare among comets in our solar system. Occasionally, under particular alignment conditions, as Earth crosses a comet's orbital path, the dust deposited along that orbit appears to extend ahead of the comet from our perspective. It's a trick of viewpoint. However, 3I Atlas doesn't align in this way. The observation angle doesn't allow for such an optical illusion, and the intensity pattern of the leading radiance doesn't align with what orbital dust would produce. David Jewitt, a UCLA astronomer who directed the Hubble imaging, examined the surface brightness relative to distance from the core. In a standard comet's envelope, the brightness diminishes steadily. The dust disperses, thins out, and the strength declines along a mild exponential curve. Yet the leading radiance of 3I Atlas declines following a projected exponential slope of -3, which equates to a 3D emission pattern with a radial decline of -4. This drop is sharper than what's seen in ordinary solar system comets, far sharper. Such a rapid decrease implies that the source of the radiance is tightly focused near the origin and fades swiftly. The substance could be ultrafine particles rapidly ejected by solar radiation forces, or there might be targeted outbursts from a particular spot on the core, forming a focused spray. DeWitt's group viewed this as dust vaporizing from the sun-facing portion of the comet. Sunlight would heat that side most intensely. Ice turns to gas, dust rises up, the dust envelope swells ahead before solar forces start driving it rearward. This explanation makes sense, though it demands uneven activity on the comet, with the sunlit half far more productive than the other areas. That degree of unevenness is uncommon, yet feasible. More challenging to account for is the lack of a dust trail. If enough dust is rising from the surface to generate the noticeable forward radiance, that dust ought to linger. Solar pressure would propel it away. The comet's speed would stretch it into a trail, and we'd detect it. Unless the dust grains are tiny, under a few hundred nanometers, they react so intensely with sunlight that they're whisked away from the comet right away, forming a dim fog instead of a clear trail. But grains that small also degrade fast under solar exposure, fragmenting into minuscule bits that become virtually undetectable. Or perhaps much of the observed radiance isn't dust, but gas. Gas doesn't create lasting trails like dust. It spreads out, dilutes, and turns clear once it drifts sufficiently from the core. But if gas mainly drives the forward radiance, that circles back to questions of makeup. Which gas, at what pace, and why so focused in one direction? Another option, which Lowe and his collaborator Eric Kito investigated in a study, involves 3 Atlas producing its own illumination instead of merely scattering sunlight. That would yield a distinct intensity distribution. Internal power sources, be it from radioactive breakdown or another mechanism, would generate output that diminishes sharply with distance as you'd be receding from the origin. This idea isn't as outlandish as it might seem. Certain comets display subtle atmospheric luminescence in their envelopes, glow from molecules energized by solar ultraviolet radiation. Yet these emissions have been thoroughly documented. Scientists understand the anticipated wavelengths, their strengths, and the associated patterns. The Hubble photograph employs broad-spectrum imaging. It gathers illumination from various wavelength bands. Absent a spectroscopic examination of that particular forward radiance, it's impossible to ascertain if it's solely sunlight reflected or if it incorporates an emissive element. Nevertheless, the configuration stands out as irregular, directed ahead with a sharp decline, lacking any matching trailing feature. Collectively, these traits form an image that clashes with conventional comet frameworks unless one resorts to exceptional conditions. And this is the key aspect. The alignment of this stream, spout, or whatever term we apply, aligns with the path of travel. The comet heads sunward, and the luminescence stretches forward along that route. Should one aim to engineer a slowdown mechanism for an extrasolar body, expelling substance ahead would generate force in the reverse direction. Admittedly, it's far less effective than conventional rocket engines, yet across extended periods with ongoing material expulsion, it might yield detectable slowing. 3I Atlas exhibits no detectable non-gravitational speeding up. Various research groups have scrutinized its path, gathered thousands of location records, and concluded that its movement aligns purely with gravitational influences. However, such evaluations carry constraints. Minor boosts under roughly 15 meters per day squared could vanish amid the data scatter, and the monitoring period remains brief. The comet surfaced in observations only during July. We have followed it over several months, covering just a segment of its path. Should it be slowing incrementally, subtly altering its course via targeted substance release, detection might elude us so far. Alternatively, the forward stream could be wholly organic, stemming from the way frozen vapors turn to gas on a fast-rotating, uneven core. The photo by itself offers no clarity, yet when paired with further oddities, the nickel outputs, the molecular makeup, the flight path, it contributes to an overall scheme in which isolated findings admit natural interpretations. Still, the combined scenario grows ever more improbable. A comet displaying atypical makeup is feasible. One with an eccentric route is possible. One venting unevenly is conceivable. Yet all these elements converging in one entity, our third confirmed interstellar guest, begins to challenge probabilistic norms, particularly once you assess its true scale. Chapter 6. 33 billion tons of enigma. As a dynamic comet expels vapors and particles, the laws of physics require a counterforce. For every action, a reaction. Debris launching from the exterior generates propulsion, modest in scale, yet quantifiable. An ordinary comet could undergo non-gravitational boosts reaching several hundred meters per day squared. Across days and weeks, this shifts the course away from a strictly orbital track. Experts leverage these shifts to gauge the extent of mass dispersal in a comet and thereby infer the heft of its central body. Heavier entities withstand boosts more readily. A compact core losing matter will swerve markedly. A substantial one shifts scarcely at all. From May 15th through September 23rd, 227 global facilities monitored 3I Atlas. Over 4,000 distinct positional readings were assembled at the Minor Planet Center, the global hub for minor body data. Richard Clue, Peter Vey, and Avi Loeb examined this collection. They matched the sightings to a gravity-only orbit, determining the comet's expected positions at every interval using just solar pull and planetary influences. Subsequently, they sought discrepancies. The ceiling for non-gravitational boosts emerged below 15 meters per day, squared, likely far lower, possibly nil, but definitely under that mark. This proves remarkably minimal for a venting comet showing clear activity. The James Webb Space Telescope scientists observed carbon dioxide venting from 3I Atlas at about 150 kilonewtons per second during early August. That amounts to roughly 13 tons daily. As the comet approached the Sun in September, the outflow rate probably ramped up. When material gets expelled at high speeds, the principle of momentum conservation means the leftover body feels a push in the opposite direction. Measurements from Webb's spectroscopic data show the escaping gas moving at around 440 meters per second. Run the math, take the mass ejection rate, multiply by that speed, then divide by the comet's total mass. The outcome reveals the expected speed-up for the comet. If 3I Atlas displayed almost no acceleration amid this ongoing shedding, its core has to be hefty enough to make the thrust too subtle to spot amid measurement errors. Those figures point to a lowest possible mass of 33 billion tons. Let that sink in. The initial interstellar visitor, 1 Oumuamua, was pegged at between 10 million and 100 million tons, based on guesses about its makeup and form. The next one, 2I Boris, probably tipped the scales at several hundred million up to a few billion tons, judging by its glow and outbursts. 3I Atlas clocks in at a minimum of 33 billion tons, and possibly much heavier that's merely the floor. It might pack 10 times that weight and still match what we've seen. This positions it as 1,000 to 1,000,000 times bulkier than the earlier interstellar wanderers. Now things get statistically awkward. Simulations of interstellar object origins and launches from star systems forecast a certain size spread. Tiny items ought to dominate in numbers over giants. This isn't just guesswork. It draws from our grasp of world-building processes, orbital tugs, and the mechanics of hurling stuff beyond solar boundaries. You'd expect thousands of 100-meter-wide drifters in interstellar voids for each kilometer-sized one. For every 100-meter piece, thousands more at 10 meters. The pattern adheres to a power law curve, spotting 1 Oumuamua around 100 meters across, aligned with expectations. Such small fry are plentiful. They're tough to pick out since they dim quickly, yet with ongoing sky surveys from observatories, we should uncover plenty. 2I Boris, being bigger and more lively, slotted into the same picture, outscaling 1 Oumuamua, but not straying far from model projections. 3I Atlas shatters the mold, drawing from that 33 billion-ton minimum. Its smallest possible width tops 5 kilometers. More plausibly, considering comet densities, it spans 5 to 10 kilometers, finds this enormous should be exceptionally scarce. Predictions indicate we'd need to spot 10,000 to 100,000 tinier interstellar travelers before stumbling on one so substantial. Yet we've only confirmed 2. Lowe dubs this a significant oddity. The term downplays it. If 3I Atlas is genuinely over 5 kilometers wide and ranks as just the 3rd interstellar body we've ID'd, then either our population models for these objects are disastrously off base, or we've been outrageously fortunate to an absurd degree, or 3I Atlas doesn't represent a typical draw from the anticipated pool. The fortune angle demands accepting odds of 1 in 10,000 or slimmer, feasible, yet unsettling. Flawed models would force an overhaul of core ideas on planetary development and dynamics, ejection routes into the void, and the mass makeup of galactic junk. Not out of the question, but it'd demand sweeping changes to frameworks that nail our other data. The atypical angle implies 3I Atlas stands out for non-statistical causes. Maybe it arose via an uncommon mechanism that spits out big bodies more often than classic formation theories allow. Perhaps it's a protoplanetary embryo, like certain experts suggest, a hefty rocky heart booted out in the system's youth. Throughout the annals of solar system visitors, nothing quite matches this. Maybe it's tracing a deliberate path that led it straight to us, turning its spotting into something planned rather than luck. That final idea unsettles the majority of stargazers, not due to sheer impossibility, but since embracing it means ditching the rule that demands we explore everyday causes fully before turning to wilder ideas. Yet, there's the rub. When do those routine accounts start seeming wilder than the other choice? Picture a comet boasting a mass 1,000,000 times beyond what's normal, emitting traces of heavy metals like from factories, spewing stuff ahead without any trailing plume behind, shining with a green hue minus the usual chemicals behind that color, matching a well-known radio burst with just a 1 chance of coincidence, and cruising by several worlds at unusually tight distances. Every oddity might have its earthly rationale. Together, though, they push the limits of belief. And we haven't even touched on the wildest quirk in its makeup yet, the finding that grabbed front-page attention exactly for bucking all our known rules on comet ingredients. Chapter 7. The Compositional Chaos. On August 6th, the James Webb Space Telescope aimed its near-infrared spectrograph toward 3I Atlas. Operating beyond Earth's air layer, Webb avoids the interference from moisture and CO2 that hampers Earth-bound infrared viewing. Its tools pick up compounds that ground scopes can't see. The analysis uncovered carbon dioxide, water, carbon monoxide, and carbonyl sulfide in the comet's surrounding haze. These are standard for a lively comet, yet the proportions were wildly off. The carbon dioxide to water balance clocked in at 8.1. Across all prior comets examined, including the earlier interstellar guest 2I Borisov, water always leads the pack. Carbon dioxide plays a supporting role, usually accounting for 5 to 20 of the easily vaporized stuff. Water frost makes up the main body of comet building blocks, thanks to its plenty in the early gas and dust clouds where these objects took shape. 3I Atlas flips that script entirely. For each water particle, 8 carbon dioxide ones appear. In terms of weight breakdown, the haze holds about 87 carbon dioxide, 9 carbon monoxide, and a scant 4 water. This setup deviates 6 standard deviations from the norm for our system's comets. In stats lingo, that's beyond a fluke, it's a whole separate category. Martin Cordner, the lead on the Webb data, suggested that such heavy carbon dioxide levels might point to formation close to the carbon dioxide frost boundary in its home system's formative disk. That's the spot around a newborn star where heat dips enough for CO2 to freeze solid. In our setup, it lies beyond the water frost zone from the sun. Bodies born in that gap could lean CO2 rich, but you'd still anticipate water as a key player, not shrunk to just 4. A different angle points to radiation effects. 3I Atlas endured billions of years adrift between stars, hammered by galactic rays. Such blasts can tweak outer chemistry, splitting water frost while sparing carbon dioxide mostly. Given long enough, a CO2-boosted crust might develop, though that'd affect just the exterior. As the comet nears the sun and starts sloughing off layers, one would figure we'd pierce that altered skin and uncover more standard mixes below. The spectral data shows no hint of such a shift. The carbon monoxide levels pose yet another riddle. At 4 times the water amount, it's boosted, though less extremely than the carbon dioxide. Carbon monoxide proves even more flighty than carbon dioxide, turning to gas at cooler temps. If the comet were merely heating and unleashing its frost by volatility order. In terms of instability, you'd expect carbon monoxide to show up prominently and in large quantities right from the start. Yet, carbon dioxide takes center stage, with carbon monoxide playing a supporting role and water vapor lagging way behind. This chemical profile points to origins that don't resemble anything in our solar system. The comet might have originated from a protoplanetary disk with a drastically altered makeup compared to the one that birthed our worlds, or it could have experienced alterations en route that reshaped its composition into an unfamiliar form. Polarization adds another layer. As light bounces off dust grains, it gets polarized. The extent and orientation of that polarization hinge on the particle's dimensions, forms, makeup, and the viewing angle. Scientists rely on polarization to deduce traits of cometary dust that are tough to gauge otherwise. A group under Zach Gray's direction examined 3 ATLAS using polarizing lenses across multiple weeks. They tracked polarization relative to the phase angle, the span between the Sun, the comet, and our planet. The findings diverged sharply from any known solar system body. 3 ATLAS exhibited intense negative polarization. At narrow phase angles, the polarized rays aligned orthogonally to the pattern seen in all other comets, asteroids, and particulate objects. The intensity of this negative effect surpassed every record in the archives. Such negative polarization arises from light interacting with grains possessing particular optical traits. Reaching the observed level, though, demands rare mixes of scale, materials, and build. The particles might be bigger than standard cometary fare, possibly featuring intricate inner designs or odd refractive qualities. Alternatively, the scattering process could deviate from our usual simulations. If the main illumination isn't just reflected sunlight, but incorporates glow from the body itself, the polarization traits shift. Gas fluorescence might generate distinct patterns beyond simple dust deflection. Still, that demands accounting for the light's source and purpose. The polarization data, the reversed chemistry from Webb, the shortage of carbon chains that nonetheless permits a greenish shine, these elements together sketch an entity that defies norms across the board. It's possible to devise explanations for each anomaly on its own. A comet born in a carbon dioxide heavy zone, dust altered optically by prolonged radiation, or surface reactions tweaked by eons in the void. Yet, unifying them all in one comet means piling improbable factors atop one another. It would have to emerge from the precise spot for carbon dioxide dominance, get hurled out at the ideal moment to endure billions of years in interstellar voids racking up radiation harm, then gather dust on voyage with optics alien to the norm, before swinging into our system on a path grazing several planets unusually close. The narrower the stipulations, the slimmer the odds. One final twist amplifies the enigma. The cyanogen find. Cyanogen, a carbon-nitrogen molecule, isn't rare in comets, but its detection intrigues given initial scans spotting it in 3 ATLAS alongside a marked lack of fellow carbon chain types like dicarbon and tricarbon. Luis Salazar Manzano from the University of Michigan pored over spectra from Kitt Peak Observatory. His crew uncovered signs of cyanogen release prior to the comet nearing the Sun, enough for robust activity. This implies cyanogen lingered in volatile states close to the surface, ready to vaporize with slight warmth. But cyanogen formation in comets, usually, it aligns with the existence of intricate organic compounds and carbon structures. Encountering it in isolation, absent the rest, comes as a surprise, akin to spotting smoke in the absence of flames. Perhaps the reactions aren't adhering to the routes we expect. Perhaps these compounds didn't form via the typical stages of comet development and maturation. Perhaps they arrived via methods we haven't yet explored. The molecular profile of 3 Atlas resembles that of a comet crafted to baffle observers. Each observation uncovers traits that individually might pass as ordinary, yet together they push the limits of what typical cosmic processes can yield. Meanwhile, as chemists quarrel over isotopic proportions and spectroscopists clash regarding spectral line shapes, Avabe has been crunching entirely different figures. Figures that render the molecular puzzle less pressing than an urgent worry over the object's potential next move. Chapter 8. The Idea of Precursor Probes. Low started with a basic orbital computation. 30 Jahrhundert. Atlas swung by within 29 million kilometers of Mars on October 3rd, yet that isn't its nearest brush with Mars's full orbit. The shortest path-crossing gap, which gauges how near one body's path draws to another's entire loop, stands at a mere 7 million kilometers. That 7 million kilometers feels enormous at first glance. It equates to about 7-fold the Earth-Moon separation. However, in the realm of celestial dynamics, particularly for something hurtling along at 60 kilometers, it's strikingly near. Near sufficient that a minor speed tweak might guide the comet straight into Mars. Low ran the figures. A path alteration of 10 to 15 kilometers executed in September could reduce that minimal gap to nothing. The comet would collide with Mars, or, at the very least, skim through its air layers. Natural comets, though, rarely execute such drastic course shifts. The gas expulsion push from a standard comet could generate speed shifts of merely a few hundred meters per second across months. Achieving 10 or 15 kilometers demands either a disastrous breakup or deliberate drive systems. Yet, this is what piqued Low's interest. Should 3 Atlas prove not to be a solitary body, should it travel with tinier elements, those elements wouldn't have to sync with the primary one's pace. A central craft deploying minor scouts could deliver substantial speed differentials. The scouts would diverge along marginally varied routes. As the core body sails past Mars at 29 million kilometers, a scout bearing the proper speed direction might actually touch down on the world. The Webb telescope gauged the gas ejection rate from 3 Atlas at 440 minutes. That represents the pace of substances naturally sublimating off the exterior. However, should an item be intentionally launched, should a scout detach from the core via engineered push, instead of heat-based vaporization, it might attain far greater velocities. A speed of 10 kilometers falls squarely within reason for a detachment action. It lies comfortably inside the range of standard rocket engines. Even a basic spring-based ejection setup could bestow several kilometers on a compact item. Thus, Low pondered, if 3I Atlas dispatched precursor probes back in September, might they make it to Mars? Affirmative, they could. Based on the moment and bearing of release, such a scout might land on Mars in as little as days or up to weeks post-detachment. At this point, it's worth considering the real-world implications. The Heresy camera aboard the Mars Reconnaissance Orbiter had been tasked with spotting 3 Atlas. It got tuned to pick up something 5 to 10 kilometers wide from 29 million kilometers away. But here got built for scanning Mars's terrain. It manages to discern details as fine as 30 centimeters, should a tinier item, perhaps 100 millimeters wide, zip by Mars from even a few 100,000 kilometers out. HiRISE could potentially spot it. That said, HiRISE had been aimed right at the projected spot of the primary comet. Should a precursor scout hail from another direction, follow an alternate route, it might slip toward Mars without notice from the very orbiter tuned to monitor. Regarding 3I Atlas, the sky views captured by the Perseverance rover gain added intrigue in this scenario. Those photos depicting potential multiple bodies, the ones examined by Stephen Burns and his colleagues, occurred during a period when the primary comet, along with any accompanying pieces, could appear together. Should those images reveal several swiftly moving entities, assuming they're not mere image glitches or stray interference, they could indicate a scattered formation instead of a solitary dense core. Low extended the analysis even more. He explored the aftermath of perihelion once the comet arcs past the Sun and re-emerges on the opposite side. Visibility from Earth-based telescopes will be blocked from late October until much of November. Perihelion arrives on October 29th at 202 million kilometers from the Sun. At that nearest point, it faces peak solar warmth, intense radiation forces, and extreme strain on its structure. For a typical comet, this phase would likely trigger significant transformations, heightened outbursts, perhaps even breakup. The core might fracture, exposing new ice that sharply increases the brightness of the surrounding haze. Gas emissions could surge as buried ices hit boiling points. If it's an unnatural entity, one able to navigate, this closest solar pass presents a tactical chance. The sun's gravity could assist in redirecting its course. A minor speed adjustment near perihelion might lead to major shifts in position over subsequent months. Spacecraft exploit such gravitational slingshots to efficiently target far-off locations. Lowe observed that targeted propulsion during perihelion would allow 3I Atlas to modify its trajectory for an Earth encounter. The object moves in a backward path, counter to the planet's orbital flow. This setup provides benefits for a collision path. No need to pursue, it's about synchronizing the meeting of two bodies heading straight at each other. A speed alteration of 30 to 40 kilometers in October might direct 3I Atlas or parts of it toward Earth from late December into early January. Could a standard comet manage 30 to 40 kilometers? No way. For an engineered vessel with engines, it hinges on size and power source. Traditional chemical thrusters would falter against those figures for an object as large as 3I Atlas. Yet we're discussing tech that may have traversed between stars, drive systems beyond our current grasp. Lowe chose his words deliberately. He avoided asserting that 3I Atlas would steer toward Earth. Instead, he highlighted the window of possibility, explaining that if equipped for it, this would be the moment and method to deploy such abilities. Then he dropped a line that every media report latched onto. Should 3I Atlas veer toward Earth upon emerging from the sun's shadow, stock markets could plummet. Consider the ramifications of that remark. Beyond the instant alarm from headlines of an inbound body, it hints at broader consequences. Proof of engineered origins, an artificial traveler from beyond our stars now nearing our world. We're no longer solitary, and whatever sent it is aware of our presence. Markets tumble amid doubt and seismic changes to our worldview. Uncovering advanced interstellar craft would unleash the greatest upheaval in our shared history. Even without immediate danger or hostile aims, realizing other sophisticated societies can access our system would upend every pillar of our economies, governments, and societies. Lowe's comment wasn't hype for dread. It acknowledged how the stakes reach well past stellar science. That's the reason Mars sightings carry such weight. That's why the quiet from NASA and ESA seems so telling. At this moment, 3I Atlas is nearing the critical phase where any surprising action on its part would have to occur soon. This is the opportunity. We simply won't have visibility into its activities until it reappears after the solar conjunction, which could take several weeks. It might have altered its path by then, or deployed untraceable payloads. It could even reveal abilities that shatter our easy belief that it's merely an odd comet. Loeb dubs it the Trojan Horse, a seemingly harmless arrival that might conceal catastrophic effects beneath its deceptively organic surface. Chapter 9. Concealed by the Sun, the Risk Period. Loeb Scale. That's what he terms it, the Loeb Scale. It's a scoring method ranging from 0 to 10, assessing the odds that an object is engineered instead of occurring naturally. A score of 0 indicates it's unquestionably natural, a fragment of ice and stone obeying standard physics, with composition aligning to familiar reactions. A 10 signifies it's unmistakably artificial. Think of something showing clear signs of tech, navigating via thrust, broadcasting emissions, or displaying forms that defy natural origins. The vast majority of space items rate 0 asteroids, comets, meteoroids, all that cosmic junk drifting around, since none hint at engineering. Oumuamua, the inaugural interstellar interloper, got a Loeb score between 3 and 5, varying by the data you prioritize. Its odd form, the extra push without evident gas release, the erratic spinall nudged it past 0, yet not far enough for solid conviction. 3 Atlas's current Loeb rating stands at 4. It can't be 0 given the pileup of oddities, the path syncing with planetary positions, the reversed chemistry, nickel absent iron, the leading spray sans trailing coma, the weight mismatch. Taken alone, each could pass as natural, but together they boost the chances of artificial origins. It falls short of 10 without irrefutable evidence. No picked-up transmissions, no spotted adjustments, no images revealing pattern designs. The thing acts sufficiently cometary that stretched natural theories still hold water. 4 lands in that ambiguous zone, probably natural overall, but the quirks are plentiful enough to keep the tech idea viable. Yet this score might shift sharply depending on events in the coming weeks. Perihelion hits on October 29th. That's when the comet swings nearest the Sun at about 1.4 AU, slightly inward from Mars's orbit. From our vantage on Earth, it'll align right in the Sun's shadow. The Sun spans roughly half a degree across our view. 3i Atlas will transit that blinding area. Earthbound scopes can't track it. Orbiting ones like Hubble and Webb must steer clear of solar proximity to safeguard their delicate gear. Observation ceases. The visibility gap spans from late October into much of November. Precise timing hinges on sightlines and the object's luminosity. But to be safe, expect no sightings for a minimum of 3 weeks. 3 weeks of intense solar exposure for the body, maximal heat pressures, and if it's built tech secrecy to execute its purpose. Upon re-emergence, we'll scrutinize for alterations. Luminosity offers the initial clue. Should the comet break apart or unleash a big flare-up, its glow will spike. Comets from our solar system often surge by multiple magnitudes near perihelion. Should 3 Atlas follow suit, it points to ordinary mechanisms at play. If it holds steady without brightening or fades somewhat, that raises eyebrows. Such behavior could signal a tougher build, more resistant to heat than standard comets. Path deviations form the next key sign. This indicator will confirm whether the object follows a trajectory aligned with gravitational forecasts based on pre-perihelion data, bolstering the idea that it's a natural body. Any divergence, such as unexpected shifts in speed or course beyond what's attributable to gravitational influences, would rapidly elevate its anomaly rating. Spectroscopic analysis could detect alterations in makeup. Has the outer layer's chemistry evolved? Have fresh substances been uncovered? Does the proportion of volatile compounds differ from prior assessments along with its overall form? As soon as 3i Atlas reappears in early December, observatories will snap images right away. Does its appearance remain unchanged? Is the leading jet feature still there? Are there signs of breakup or division? In the meantime, Low isn't merely theorizing outcomes, he's actively scanning the heavens. The Galileo project runs 3 facilities, one in Massachusetts, another in Pennsylvania, and a third in Nevada. These sites feature broad-view cameras, heat-sensing detectors, and software for automatic spotting of airborne anomalies that don't resemble typical planes or earthly items. The initiative mainly targets unidentified anomalous phenomena, or UAP, formerly known as UFOs. Yet with 3ILAS nearing its closest solar approach, Low has implemented a dedicated surveillance routine. Should the entity prove to be a carrier vessel releasing subordinate craft toward our planet as it arcs past the Sun, those subordinates could reach us anywhere from weeks to months afterward. Thus, December into January forms a period when bizarre sky events might surge. The Galileo project's gear will operate non-stop, recording oddities, hunting for trends, seeking entities traveling quicker than orbiting satellites, exhibiting maneuvers surpassing known aviation capabilities, or showing up in clusters or at moments tied to 3i Atlas's solar closest point. It may resemble tales from speculative fiction. In a way, it draws from imaginative narratives. The key distinction lies in our use of actual observations, precise computations, and tangible entities we can image and quantify. If Low's views are off base, if 3 Atlas is merely an odd comet with mundane rationales for its quirks, then the Galileo project will pick up nothing out of the ordinary. The body will swing out from solar occlusion, a bit more luminous, perhaps in pieces, adhering to its forecasted route. The nickel signals will trace back to some rare chemical process. The path's odd alignments will get chalked up to observational biases in spotting interstellar visitors, and daily existence proceeds unchanged. Should he be correct, even in part, December could mark one of humanity's pivotal eras. Not due to tales of assaults or aggression, Low steers clear of such portrayals. Even engineered artifacts might represent neutral exploratory devices from societies uninterested in meddling. Rather, validation would upend all foundations, recasting our cosmic position. Queries on solitude would find resolution. Choices regarding funding, long-term planning, and priorities would unfold. Knowing interstellar traversal is feasible, other minds thrive, and in the deepest way, we hold no unique status. Indeed, the JUICE probe, en route to Jupiter, will examine 3 Atlas toward the end of November. From November 2nd to 25th, JUICE will direct its tools at the comet shortly post-perihelion, as it exits the sun's blinding light yet stays highly energetic. JUICE includes imaging devices, spectrum analyzers, and detectors for particles. Though positioned more distantly than Mars Vantage, it benefits from timing during maximal vigor, when signals peak most vividly. JUICE's findings won't reach Earth until February, as the craft sits on the sun's opposite side. Employing its main antenna as the heat shield is relying on a secondary low-speed communication channel. As a result, we're stuck waiting for several months while those readings trickle down and get crunched. But the info is inbound, and it could reveal exactly what 3I Atlas got up to out of sight from Earth, its appearance during that peak of frenzy, and any shifts that demand our attention. Right now, though, everything's shrouded in mystery, both in the literal sense and the metaphorical one. The bizarre entity that stumped skywatchers for months is set to vanish, eclipsed by the blinding glare of our sun, carrying on with its unseen business. And upon its return, should it emerge transformed or bearing hints of purposeful behavior, Lowe's score jumps from 4 to 5, or even beyond. Our debates over its possible artificial origins would pivot to pondering its motives and how we ought to react. Chapter 10. The Secrets They're Keeping. Space organizations follow a familiar cadence when unveiling breakthroughs. Drafts of announcements roll out. Researchers sit for media chats. Unrefined datasets flood open databases. Official social feeds spotlight the gems. The whole setup promotes clarity, stirs widespread fascination, and bolsters the budgets fueling these ventures. Yet when that cadence falters, when anticipated scans wrap up but outputs vanish, when probes get met with fuzzy talk of further evaluation, folks start paying closer heed. NASA's dedicated hub for 3I Atlas catalogs the tools that have tracked or intend to track it: Hubble, Webb, TESS, SWIFT, SPHEREX, Perseverance, Mars Reconnaissance Orbiter, Curiosity, Europa Clipper, Lucy, Psyche, Parker Solar Probe, Punch, SOHO, and ESA's JUICE. That's a formidable collection. Virtually every active orbital scope and deep spacecraft has swung its gaze toward this thing at one juncture or another, yet the data drops lag far behind the scanning calendar. Webb's August spectral breakdown hit the scene swiftly, dropping as a preliminary paper in mere weeks. Hubble's July snapshot went live. SPHEREX data on carbon dioxide releases got disseminated. Then October rolled in, and the pipeline went dry. The Mars sweeps from October the 1st to 7th should have been a breeze to publicize. Orbiters around the red planet customarily beam images out in days. The HiRISE portal routinely refreshes with fresh planetary shots every couple of days, or even daily amid intense monitoring pushes. But zero from the 3I Atlas close approach has materialized. The ESA runs on separate bureaucratic tracks from NASA-distinct budgets, varying supervision, unique mandates for outreach. When the pair clamps down in unison on a shared focus, it points to alignment. That alignment might spell partnership, experts across the outfits pooling insights, opting to pause announcements until the full dataset's dissected. This makes sense for intricate probes, where early takeaways risk getting twisted. Alternatively, it could signal deliberation, stumbling on the unforeseen, sparking talks on framing the reveal, supplying backdrop, and locking in extra confirmations before broadcasting. The hush from Simeon Schmaus, the avid astrophotographer who boasted of catching preliminary peaks in October 1st, captures, piles on intrigue. Hobby sky gazers generally trumpet their hauls with gusto. The scene pulses with speedy exchanges, collective vetting, and shared dissections. When an individual falls silent after dropping a tantalizing nugget, It boils down to a duo of possibilities. They spotted a blunder and feel chagrined, or they unearthed a bombshell and are gearing up for a polished rollout. Schmaus hasn't disavowed his sightings. No amendments have surfaced. He's merely gone mum. In the interim, enthusiast astronomers press on, tinkering with the scraps that's out there. The openly shared perseverance. The artificial hypothesis is gaining traction. JUICE will monitor it in late November amid peak post-perihelion activity. The Europa Clipper, en route to Jupiter, could capture sightings too, based on orbital alignment and mission schedules. These probes offer views of the comet from perspectives and ranges impossible for ground telescopes. Their findings will trickle in over time, get analyzed, and ultimately shape our knowledge. But that takes time we don't have yet. For the moment, we're stuck in a void, the space between captured images and public releases, between backyard finds and verified reports, between the puzzles we're pondering and solutions buried in inaccessible datasets. Meanwhile, as we linger in that limbo, 3I Atlas presses on, drawing nearer to the sun, warming up, ramping up its outbursts, perhaps unleashing surprises we'll only uncover weeks later when it swings back into view and reveals its transformations. So here we sit, gazing at a blank patch of sky concealing something remarkable on the far side of our star. 3I Atlas is out there at this instant, nearer to Sool than in billions of years, soaking in gigawatts of sunlight, maybe breaking apart, maybe shifting course, or simply behaving like any ordinary comet from the dawn of the solar system. We've charted its trajectory from the solar system's fringes, pinpointed its position during the WOW signal's arrival on Earth, quantified the bizarre ratios in its makeup, noted the anomalous metals, sketched the tail-defying expected directions. We've tallied the odds-defying stats, piled up the oddities, and ended up in a realm where solid conclusions seem forever out of reach. Perhaps it's merely a comet and oddball, sure, but a straightforward cosmic wanderer obeying physics as we know it. The quirks will sort themselves out. The absent info will surface and explain everything. Come December, it'll emerge just as forecasted, a bit more luminous, sticking to its orbit, proving the cosmos still follows logical rules. Or perhaps this is the harbinger of a discovery that upends our views on humanity's spot in the universe. In any case, the coming weeks will reveal the truth, and we'll be right here to witness it. Thanks for sticking with this tale, for chasing these enigmas into the unknown, for embracing the unknown rather than settling for pat explanations. If this sparked your interest, hit like and subscribe to catch the updates when 3I Atlas reemerges and we uncover its secrets. As ever, this is for learning and enjoyment. The facts and sightings are legit, but our takes are just hypotheses. Dig into it yourself. Challenge every idea, even those shared here. For now, 3I Atlas glides quietly in the sun's shadow. December draws near. Hobby scopes are primed. Major facilities have slots booked. Galileo project gear is logging data. And out in the void, an interstellar visitor forges ahead, oblivious to our curiosities, speculations, dreams, and dreads over its true nature. Rest easy, ponder far-off suns, and keep in mind that reality has always outstripped our wildest fancies. Good night. Imagine this scene unfolding right this second. Some 620 light-years distant, a Jupiter-sized world is devouring matter, not gently or methodically, but with savage 4.6 billion tons of gas and debris every second, pouring into an entity that defies easy labels, straddling the boundary between planet and star. At the same time, much nearer, on a neighbor we've probed for ages, a rover roughly car-sized has spotted a clue in a stone that could hint at extraterrestrial biology. And in labs worldwide, scientists on Earth have broken through a long-standing obstacle in quantum computing's past, crafting a device capable of operating indefinitely. In theory, this unlocks possibilities we believed were years from realization. Yet what renders this week so peculiar is the contrast. As we uncover these vast astronomical breakthroughs, we're simultaneously revealing hidden truths within our own physiology that we never imagined. Everyday adipose tissue has been exposed in the act, dispatching signaling molecules straight to our brains, molecules that could be forming the amyloid deposits responsible for eroding our recollections. and venturing deep into the past, prior to any of this holding significance, before humanity emerged, before dinosaurs roamed, before the initial trees sprouted, a dominion dominated our world for almost 1 billion years. Neither fauna nor flora, but rather fungi, the concealed builders who shaped the environment we now occupy. This isn't speculative fantasy. This is the essence of the current week. Should these enigmas draw you in, give that like button a tap and sign up for updates. Next, drop a comment sharing your listening location, the local time, and which revelation most disrupts your grasp of existence. To support our group's expansion, spread the word via X, Facebook, Reddit, or your chat apps. We appreciate your steadfast support. Chapter 1. The Leopard-Patterned Stone. On July 23, 2024, a rover called Perseverance drove its drill into a Martian boulder. This stone bore the moniker Chava Falls, selected by the Earth-based crew who had monitored it closely for several months. Their interest was justified. Positioned along the rim of an ancient riverbed, a waterway that long ago funneled swift currents toward a basin containing a lake over 5 billion years old, the site alone wasn't the sole draw. The surface design compelled their halt. Dark dots encircled by lighter halos dotted the rusty surface, reminiscent of a leopard's coat. Nothing comparable had appeared before. The tool extracted a core specimen, a rock tube roughly pencil width in diameter, and encased it for possible transport back home. That's when the intensive analysis kicked off. The vehicle housed tools to scrutinize the stone's composition, sans unsealing the container. Their revelations continue to reverberate across the research field even now. Within those spots lay iron and phosphate. Amid the whitish calcium sulfate layers, hints of hematite emerged, the very compound tinting Mars crimson. Yet in this specimen, an alteration had bleached the crimson hue. Such transformations liberate iron and phosphate. Moreover, they generate power sources akin to those fueling microorganisms. A study surfaced in Nature on September 10, 2025. The researchers had devoted 12 months to scrutinizing the information, conducting experiments and verifying results repeatedly. They highlighted 2 distinct compounds, vivianite and grage, forms of iron phosphate and iron sulfide. Here on our world, these arise in low oxygen settings where bacteria process organic materials, leveraging reactions for sustenance. The configurations aligned, the elements aligned. Every aspect of this boulder pointed to a mechanism that, terrestrially, would scream biological origins. NASA's interim head convened a media briefing. Following extensive evaluation, he declared no alternative rationale surfaced. To the global audience, he announced, "This might represent the strongest indicator of extraterrestrial biology we've detected on Mars to date. No definitive confirmation yet, but the nearest we've grasped through our mechanical proxies." The press frenzy ignited. Front pages blared tales of extraterrestrial bacteria and primordial Martian organisms. Researchers, however, proceeded with caution. They employed a phrase that feels clunky, yet bears profound implications. Potential biosignature, an indicator possibly crafted by living processes, though demanding further validation. Further investigation is required before experts can draw firm conclusions. This is the point where the narrative becomes deeply aggravating. The specimen resides within Perseverance's core, enclosed in its container, alongside 24 additional specimens gathered from various sites throughout Jezero Crater. To definitively determine the origin of those leopard-like markings, researchers must transport that stone back to Earth. They require analysis using equipment far more precise than what we can deploy to the Red Planet. Mass spectrometers, electron microscopes, and instruments that occupy whole labs are essential. A dedicated initiative exists precisely for this purpose, known as Mars Sample Return. However, the project faces significant challenges. Estimates for its cost have escalated to between $8 and $11 billion. The schedule has extended to 2040 or later. Political transitions, evolving priorities, and funding limitations have followed. Currently, Mars Sample Return lingers in uncertainty, not canceled, but not progressing fully either. Thus, A stone on Mars potentially holding traces of ancient life remains there, with no straightforward plan to retrieve it. Chapter 2. The world that consumes like a stellar giant, located 620 light-years from our planet in the Chameleon constellation. An entity exists there that defies expectations in its behavior. It bears a catalog identifier rather than a proper title. Quais J and TAR 249 Planet 8101, a sequence of digits and symbols that skywatchers employ to index cosmic discoveries. This body possesses a mass ranging from 5 to 10 times that of Jupiter, the colossal orb in our own system. Such heft classifies it solidly as a planet, yet it circles no sun. Instead, it wanders solo across the void, one among the estimated trillions of free-floating rogue planets meandering the Milky Way, adrift in the interstellar shadows. For a long time, experts assumed these wanderers were frigid, silent, inactive bodies, either ejected from stellar systems or condensed from insufficient gas clouds unable to spark nuclear fusion, remaining faint and ordinary forever. EY's J. Count 49 shattered that view. In spring 2025, observers directed the European Southern Observatory's Very Large Telescope at this entity. They observed a serene scene, a youthful sphere encircled by a ring of gas and debris, remnants of its birth. This ring was nourishing the planet gradually via accretion, debris cascading onto its exterior, incrementally boosting its size. That's standard procedure, that's planetary development. But come August, the situation shifted dramatically. The planet started ravaging its encircling disk, not steadily, but with ferocity. The influx rate surged eightfold compared to mere months prior. 6 billion tons of matter per second cascading into this isolated sphere amid the emptiness. To grasp the scale, picture Mount Everest's full bulk vanishing into it every several seconds. This voracious phase persisted for a minimum of 2 months, and as the study appeared on October 2, 2025, the activity showed no signs of stopping. The principal investigator, astronomer Victor Alves Medeiros Abad, offered a remark that encapsulates the oddity. Folks often view planets as serene and steady realms, he noted. Yet this finding reveals that free-roaming planetary mass bodies in the cosmos can turn out to be thrilling locales. Thrilling might downplay it. What TY's J1249 is up to has previously been witnessed only in nascent stars and brown dwarfs, entities hefty enough for intricate magnetic processes. This marks the most intense accretion event documented for any planetary mass object throughout astronomical records. Even more peculiar, the observers identified indicators of magnetic forces propelling this material plunge. Potent fields channeling vapors and particles to the planet's crust, akin to unseen cosmic thoroughfares. We typically link such mechanisms to stars, not worlds. Stars boast the bulk and inner motions to produce robust magnetic zones. Planets, particularly free-floating rogue planets wandering solo, shouldn't be forming new material. But that's exactly what's occurring right before our eyes, impossible to ignore. Observations uncovered traces of water vapor in the planet's atmosphere right amid the outburst, along with hydrocarbon compounds that morphed their structures as the accretion ramped up. Evidence of intense heat and chaos reshaping the disk's chemical makeup. Now, experts are revisiting a puzzle they assumed was settled. What's the origin of these nomadic worlds? The leading explanations involve either being hurled out planets-born, orbiting a star only to get flung away through gravitational tugs or formation via direct gravitational implosion. In the latter, a gas cloud in the void crumples under its own pull, yet falls short of the heft required to ignite as a star. Should ejection hold true, such worlds ought to be frigid husks, stripped of their birth disks ages ago. Yet Char 107 retains its disk intact. It's actively expanding, acting more like an entity that coalesced right there in isolation, drawing from a nebula much as a star does, just halting before reaching fusion threshold. This muddies a boundary we once saw as distinct. How do we separate the tiniest stars from the mightiest planets? Our criterion hinged on nuclear fusion, whether something can keep hydrogen fusion alive at its heart. Yet if planetary-scale bodies can emerge star-like, develop star-like, and harness magnetic forces star-like. Perhaps that divide isn't so crisp. There could be a continuum, a smooth transition from planet to star, with outliers like Char 107 occupying that hazy zone, challenging our neat labels. The scientists suspect we're witnessing planetary genesis unfold live, observing a realm assembling itself amid the starless void. And it's proving far wilder, far more ferocious than models ever foresaw. Chapter 3. The Device That Runs Endlessly. Deep in a Harvard University lab sits a contraption that's operated non-stop for more than 2 hours. That alone might seem mundane, but grasp its nature, and it transforms. This is a quantum processor. Throughout quantum computing's past, such systems suffered a crippling defect. They halt not from any manual shutdown, but because their core elements, the qubits powering the magic, simply evaporate. Experts term it decoherence. The qubits shed their exotic quantum traits and turn inert. Initial prototypes managed mere milliseconds of uptime. Cutting-edge versions pushed it to about 13 seconds tops. Then came the resets, the reboots, the fresh starts. But the Harvard group, under Professor Mael Lukin's guidance, engineered a game-changer. Come September 2025, they detailed their work in Nature. Their setup boasts 3,000 qubits and operates seamlessly, no pauses or reboots for however long power flows. In principle, it might endure indefinitely. Far from a minor tweak, this represents a core revolution reshaping quantum potential. Let me explain the hurdle they cleared. These machines harness atoms or tinier particles, suspending them in precarious quantum overlays that encode myriad states simultaneously. That's the edge granting them supremacy, cracking select challenges orders of magnitude quicker than traditional rigs. Still, those overlays are perilously delicate. They demand cryogenic chill, brushing absolute zero. They need shielding from shakes, rogue EM waves, any intrusion at all. Despite such safeguards, qubits inevitably crumble. They bleed data, their states crumble, the quantum essence unravels, and the run terminates. Over 5 years, the Harvard crew tackled this beast. They devised a technique relying on an optical lattice conveyor and laser-based tweezers. These employ pinpointed light beams to seize lone atoms and shuttle them with stunning accuracy. Their key insight came in unraveling replenishing qubits. During operation, involves injecting fresh atoms to offset those that exit the system. The device incorporates up to 300,000 atoms each second, which outpaces the depletion of qubits by a wide margin. At this point, there's essentially no barrier to the extended runtime of these quantum processors. One team member, researcher Toot Wong, shared a notable insight during an interview. He noted that while scaling up from our current position will take effort, the pathway forward has become evident thanks to the innovative tests conducted at Harvard. That clear pathway carries weight in an area plagued by unpredictable advances and deferred deadlines. Another partner, an MIT physicist by the name of Vladenik, offered even greater detail. Prior to this development, he mentioned, experts thought non-stop quantum systems were still at least 5 years out. Today, it feels far nearer, perhaps just 2 to 3 years off. Consider the significance of that shift. In as little as 2 to 3 years, quantum machines could function much like the everyday classical devices we rely on. Not setups that operate briefly before rebooting, but systems that remain active, build up data over time, and handle tasks demanding prolonged, uninterrupted processing. The effects extend into numerous disciplines. In pharmaceuticals, for instance, these computers might model molecular bonds that defy classical computation. In encryption, they could shatter safeguards securing worldwide data flows. For machine learning, they might refine neural architectures beyond present capabilities. Fields like materials engineering, economic forecasting, weather modeling, and beyond, anywhere intricate challenges surpass conventional processing limits. Yet, this narrative has another dimension. Google recently grabbed headlines in quantum research by employing a 58-qubit processor to generate and detect a topological ordered state in a fluid. This material phase, long hypothesized but unobserved, emerges solely in a quantum setup driven by steady periodic forces, yielding a non-equilibrium condition beyond standard physical models. The team observed unusual particles evolving live, validating concepts on matter's response when driven far from balance. Such investigations highlight what quantum hardware unlocks. Beyond mere speedy computations, they open fresh avenues for probing the essence of physics. Chapter 4. The Fat Communicating with Your Brain. Right now, within your body, a process unfolds that experts have only recently uncovered: your adipose tissue. The padding that safeguards organs and holds energy reserves isn't idle. Instead, it's communicating, not through speech, of course, but via chemical signals, minuscule membrane-bound parcels circulating in your blood. Known as extracellular vesicles, these carriers transport payloads including fats, proteins, and genetic material. They navigate past vessel linings and surmount obstacles impenetrable to typical compounds. And now, studies confirm that certain ones reach the brain entirely. Researchers at Houston Methodist, under the guidance of scientist Stephen Wong, released their results on October 3, 2025. The group gathered adipose samples from slender and overweight participants, extracted the emitted vesicles, and scrutinized their contents. The fat payloads varied notably. Particular lipid types appeared in higher concentrations within vesicles from those with obesity, such as lysophosphatidylcholine and sphingosine. Next, they performed an ingenious test. They introduced these vesicles to amyloid beta peptides, the sticky proteins that build up into plaques in Alzheimer's-affected brains. The vesicles originating from obese tissue spurred quicker clumping of those proteins at a markedly accelerated rate. The lipids inside hastened the buildup mechanism, the very mechanism thought to fuel neurodegeneration. This isn't mere association, it's a direct process. Scientists demonstrated that adipose tissue can transmit signals straight to the brain, influencing the speed at which the signature damage of Alzheimer's develops. For years, excess weight has been recognized as a contributor to Alzheimer's risk, yet the connection remained vague, often routed through factors such as swelling or impaired insulin response. Now, this research establishes a straightforward path. Adipose cells release tiny packets called vesicles. These vesicles penetrate the blood-brain barrier. Loaded with fats, they encourage the buildup of plaques. It's a clear route, a biological link tying the body's fat reserves to the mind's worst affliction. Around the same period, a group at Purdue University released connected results. They examined brain tissue directly, focusing on microglia, the guard cells meant to safeguard nerve cells. In normal brains, these microglia roam vigilantly, removing waste, combating invaders, and keeping equilibrium. However, in Alzheimer's-affected brains, the microglia nearest to amyloid plaques appeared altered. They were bloated, packed with fat globules, lipids gathering within the cells. Under the guidance of Professor Gareth Chopra, the team discovered that these lipid-laden microglia lost their effectiveness. They failed to eliminate plaques. They couldn't shield neurons. Essentially, they were immobilized by their own fat overload. The group mapped the chemical sequence. Upon facing plaques and inflammatory signals, microglia begin generating unbound fatty acids. Under typical conditions, they'd burn these for energy. But during illness, the process derails. An enzyme known as DGAT2 transforms those free fatty acids into triglycerides, fat's stored version. It produces so much that the microglia get overwhelmed. Fat droplets accumulate. The cells lose mobility. Functionality halts. Chopra labeled these buildups as lipid plaques, a phrase mirroring the amyloid plaques that draw all attention, yet highlighting a separate issue, a concurrent disorder ignored for more than a century. Here's the key development. The scientists evaluated two compounds, one inhibiting DGAT2 and another accelerating its breakdown. The breakdown method succeeded. It lessened the fat accumulation. It revived the microglia's capacity to devour amyloid plaques. It enhanced signs of neuron vitality in Alzheimer's animal studies. This points to a fresh therapeutic angle, not assaulting the amyloid directly, but tackling the fat processing that disables the brain's protectors. It unlocks an avenue that drug firms have overlooked, an entrance linking Alzheimer's studies to fat science, metabolic disorders, and the 40 of Americans grappling with obesity. Consider the broader impact. For decades, Alzheimer's has been viewed as a matter of faulty protein-folding amyloid plaques, tau tangles, and brain swelling. Countless medications aim to dissolve plaques or stop their creation. Most flopped. Perhaps they targeted effects rather than roots. Maybe the true instigator lurks openly in the fats crowding our cells and dispatching signals we never suspected. Chapter 5. The realm that readied the planet. Prior to forests, prior to grasslands, before the initial lichen adhered to a damp stone by the sea, another entity existed, not idle, but active, eroding rock, recycling elements, laying the molecular groundwork enabling all that followed. We envision terrestrial life kicking off with vegetation, verdant trailblazers claiming a desolate terrain. But the terrain wasn't empty upon plants' arrival. It had been cultivated over hundreds of millions of years by a domain we scarcely acknowledge: fungi. On October 1st, 2025, researchers from the Okinawa Institute of Science and Technology released a study in Nature Ecology and Evolution that reshapes our understanding of life's history on land, drawing on fossil data alongside an innovative method based on horizontal gene transfers. These are genetic elements that shift laterally across species, bypassing the usual parent-to-offspring inheritance. The findings push the roots of fungi far deeper into the past than previously thought. The shared forebear of every existing fungus likely thrived between 1.4 billion and 900 million years ago. For context, terrestrial plants didn't emerge until about 470 million years back. That means fungi could have been evolving and spreading for nearly 1 billion years prior to the arrival of the earliest greenery. This isn't a minor tweak, it's a complete overhaul of the narrative. Multicellular complexity, where organisms consist of numerous cells each performing distinct roles, arose separately on our planet precisely 5 times. Those lineages include animals, terrestrial plants, fungi, red algae, and brown algae. Every one of these clades devised unique ways for their cells to adhere, exchange signals, and form structured tissues. In many cases, the fossil record offers solid dating markers. For instance, animals first appear roughly 600 million years ago in sites like the Ediacaran, marked by their signature traces. Red algae might date to as far as 1.6 billion years ago, preserved in ancient seaweed-resembling remnants from India. Yet fungi rarely fossilize well. Their delicate filamentous structures decompose rapidly, leaving evolutionary dating riddled with gaps. The team, headed by scientist Gergely Salasi, turned to horizontal gene transfers as chronological anchors. Such a gene leap from one fungal branch to another sets a boundary. The source lineage's common ancestor predates the receiving ones. Spotting 17 instances of these events and weaving them with the limited fossils, the group pinned down the fungal chronology with remarkable accuracy. The result paints fungi as a realm that ruled continental landscapes for an astonishingly vast duration. Consider the implications. Over hundreds of millions, perhaps nearing 1 billion years, fungi stood as the pinnacle of terrestrial complexity. They weren't isolated. Oceanic algae thrived in the seas and probably along nearshore zones, while bacteria built filmy communities. But fungi stood apart, conducting biochemical feats unmatched by others. They release enzymes to dissolve rock, freeing up phosphorus and vital minerals trapped in stone. Their mycelial webs link remote soil areas, ferrying essentials over wide terrains. They forge alliances with fellow life forms, swapping nutrients for carbohydrates and mutualistic bonds that aid everyone involved. The study uncovered signs that certain ancient fungi possessed pectin-degrading enzymes key to dismantling plant cell barriers as early as 1.2 billion to 800 million years ago. This hints at early associations with algae, possibly aiding their endurance in the tough interface of sea and shore. When plants eventually developed and ventured onto landmasses, they encountered no empty canvas. Instead, they stepped into an environment molded by fungal influence. rudimentary soils with ongoing nutrient loops and active geochemical processes. This upends the idea of plants as lone trailblazers. Rather, they stepped into a domain that fungi had been reshaping for ages. And upon their debut, plants swiftly linked up with fungi. These alliances, known as mycorrhizae, are ubiquitous. Today, 90% of terrestrial plants host fungal companions in or near their roots, bartering carbohydrates for minerals. It's conceivable and probable that such symbioses were essential for plants to claim the continents. Those connections may trace their origins in both practical and phylogenetic senses to the era when fungi initially engaged with algae in the primordial shallows. Chapter 6: The Vinegar That Deceived the Globe. Back in March 2024, researchers from Lebanon's Holy Spirit University of Kazlik released a modest clinical study in the BMJ Nutrition Prevention Health Journal. The experiment featured 120 adolescents with an average age of 17, each carrying excess weight or classified as obese. These volunteers got split into 4 cohorts. 3 of the sets consumed apple cider vinegar every morning, doses of 5, 10, or 15 milliliters, stirred into water and downed prior to meals. The remaining cohort got a sham version, a placebo vinegar, mimicking the real thing in appearance and flavor, but missing the key component, acetic acid. The experiment ran for 12 weeks. The findings, as detailed in the article, proved astonishing. Those sipping the vinegar shed substantial pounds, averaging 6 to 8 kilograms, with the highest dosage yielding the most dramatic reductions. Their body mass indexes dropped noticeably, as did measurements around their waists and hips. Levels of blood sugar, triglycerides, and cholesterol all showed positive shifts. The authors proposed that apple cider vinegar delayed stomach emptying, fostering satiety and curbing hunger. They included graphs and statistical breakdowns, highlighting stark, meaningful contrasts between the vinegar cohorts and the placebo one. The journal issued a press statement alongside the publication, and news sources worldwide swiftly amplified it. Front-page stories hailed an easy, affordable fix for the obesity crisis. This everyday kitchen staple, apple cider vinegar, emerged as a supposed wonder cure for slimming down. The research exploded in popularity. Pieces proliferated across platforms. Online personalities started touting morning vinegar routines. An industry already topping $1 billion in value experienced a fresh surge of attention. Folks referenced the study in online discussions, personal blogs, and casual chats with acquaintances. It carried the authority of peer-reviewed research from a BMJ Group outlet, a powerhouse in health literature. Yet from the outset, certain experts harbored doubts. James Heathers, a specialist in research ethics, dove into the document soon after its debut. His review uncovered disturbing issues. The age ranges and BMI figures across the groups mirrored each other almost exactly, a statistical anomaly. Random group assignments typically produce some discrepancies, but these divisions appeared overly uniform, more like deliberate calibration than chance allocation. In a May 2024 breakdown, Heathers flagged these improbable data trends. He noted that, if accurate, the vinegar's impact would outpace semaglutide drugs by 50 meds that demand hefty prices and doctor's orders. A mere spoonful outperforming state-of-the-art treatments pushed the boundaries of belief. Fellow scientists voiced worries via correspondence to the editors. The trial hadn't undergone prior registration, violating BMJ Group's guidelines meant to block cherry-picked outcomes. The stats techniques lacked clarity. Efforts to rerun the calculations using the shared figures fell short. BMJ's Integrity Unit initiated a probe, handing the manuscript to outside experts for a thorough check on validity and reproducibility. The analysts couldn't duplicate it. They spotted several computational flaws and oddities in the dataset, hinting at the need for external validation of the source material. The figures simply didn't align. On September 23, 2025, 18 months post-release, the journal pulled the article. The withdrawal statement cut straight to the chase. The outcomes lacked trustworthiness, riddled with numerous inaccuracies, and impossible to confirm. The writers, in reply, attributed the issues to inadvertent oversights and concurred with the decision. The choice to withdraw the paper came too late. The harm had already spread. Over the course of 18 months, that research served as key support in various citations. It showed up in comprehensive overviews and combined analyses that synthesized findings from numerous investigations to reach wider insights. One particular overview, released just prior to the withdrawal, drew partially on the faulty information to propose that apple cider vinegar could aid in controlling body weight. Now that overview stands tainted, resting on a base that incorporates invented or severely erroneous outcomes. An editor from the BMJ Group, Helen McDonald, issued a clear public declaration. While it's appealing to inform the public about what seems like an easy and effective method for shedding pounds, she noted, currently the study's findings cannot be trusted, and reporters along with others ought to avoid citing or relying on those findings in any upcoming coverage. Yet, countless pieces linger on the web without updates, continuing to reference the pulled-back work, and to how many individuals altered their habits relying on details that proved untrue. Chapter 7. The Moon's Split Soul. Our satellite boasts dual aspects, and they're far from identical. Even a basic telescope reveals this divide. The side perpetually facing Earth features shadowy regions known as Maria, vast ancient lava fields that once flooded crater basins eons ago. The opposite side, concealed from direct sight until probes orbited around it, presents an entirely distinct terrain. It has far fewer Maria, abundant craters, and a surface that seems more aged with less reshaping from eruptions. For years, this imbalance has baffled experts in planetary science. How could the two halves of the moon vary so starkly? After all, they belong to one entity, born from identical stuff, molded by shared celestial events, or at least that's the assumption we held. On October 3, 2025, scientists unveiled an examination of moon rocks gathered from the far side via China's Chang'e 6 expedition. These marked the inaugural samples retrieved from that region, and their revelations challenge long-held views of the moon's core makeup. The specimens abound in crystals born from liquid rock that solidified over time. However, their makeup deviates notably. They hold reduced levels of heat-generating substances, lower amounts of radioactive forms of potassium, thorium, and uranium compared to near-side equivalents. This matters greatly, as such elements sustain a world's inner warmth. Across billions of years, their breakdown unleashes power that fuels eruptions, liquefying stone and propelling it outward. The team determined that the far side emerged from magma that was markedly chillier, not just a touch cooler, but profoundly so. This points to a moon interior lacking evenness. Rather than a straightforward orb with symmetrically stacked layers of crust, mantle, and core, it harbors deep-seated unevenness. Variations in makeup and heat between the facing and hidden sides trace back to the moon's very origins. The primary explanation for the moon's birth centers on a massive collision about 4.5 billion years ago in Earth's formative era, a body the size of Mars smashed into our world. The crash was ferocious enough to vaporize material, spawning a swirling ring of wreckage encircling the planet. Gravity drew that rubble into cohesion, birthing the moon. But the formation wasn't even or seamless. Initially, the moon probably existed as a ball of melt, solidifying gradually across millennia. During cooling, heavier compounds descended, while buoyant ones rose, forming strata. Fresh evidence indicates this layering unfolded unevenly across the hemispheres. Maybe the earthward face absorbed extra warmth from tidal stresses as our planet's stronger gravity tugged and heated its depths. Or initial radioactive distributions might have been lopsided, clustered denser on one flank. Regardless of the reason, the discovery points to a moon harboring a bifurcated core. This finding reaches far beyond the realm of lunar rock formations. It offers insights into the origins and transformations of rocky celestial objects. We usually depict planets and satellites as balanced globes with consistent internal strata for our simulations. Yet, if the moon, compact and straightforward by planetary standards, displays such striking internal disequilibrium, what does that imply for other celestial entities? Mars exhibits dramatically contrasting hemispheres. The northern plains are even and polished, the southern plateaus weathered and riddled with impact scars. Might Mars conceal an uneven core with divergent heating timelines across its divisions? And what of exoplanets? The vast array of planets we've detected around remote stars. Their depths elude direct observation. Still, if such imbalances are typical, our foundational theories could be profoundly misguided. The gathered materials disclosed yet another revelation. They verified that eruptions on the Moon's far side wrapped up ahead of those on the near side. Devoid of ample radioactive elements, the far side couldn't prolong its molten outbursts. It hushed down even as the near side kept venting, pouring magma into depressions. This etches a stratigraphic ledger, a chronology inscribed in stone, tracing the Moon's thermal reserves as they ebbed over billions of years. Analyzing these specimens allows experts to sharpen predictions about global heat dissipation or the span needed for a planet to solidify from within and lapse into geological stasis. Chapter 8. The Frost Veiling a Sea. Saturn possesses a multitude of satellites, but one continually pulls experts in, fuels media buzz, and whispers of potential companionship in our cosmic backyard. Enceladus, a modest orb spanning just 500 kilometers, sheathed in gleaming ice that mirrors virtually every beam of solar light. At first glance, it seems untouched, encased in perpetual freeze, devoid of vitality. However, in 2005, the Cassini probe ventured near enough to reveal the reality. Enceladus isn't dormant, it's actively spewing. From fissures around its south pole, massive sprays of water vapor and frozen flecks propel outward into the cosmos. Jets climbing hundreds of kilometers skyward, these aren't fleeting bursts. They endure steadily, ceaselessly, driven by a hidden reservoir below the surface, a planet-wide expanse of fluid water, stretching tens of kilometers downward, capped by an icy layer possibly 20 to 30 kilometer deep. Tidal forces preserve the sea's fluidity, much like the orbital tugging that ignites Io's fiery surface on Jupiter. Saturn's pull contorts and kneads Enceladus during its path, sparking internal rub that yields warmth, thawing material that distance and chill should have locked away forever. Cassini plunged amid the sprays, sampled their makeup via its sensors, and dissected the elements. The outcomes were breathtaking. H2O, naturally, alongside salts, traces of seafloor mineral exchanges, minuscule silica flex grains of silicon dioxide forged by scalding fluids, meeting stone at over 90 C. And carbon chains, starting simple, with methane, carbon dioxide, carbon-infused substances, sans clear signs of biology. Follow-up sweeps uncovered richer variants like propane, ethane, acetylene. And lately, based on a recent dissection of Cassini records from October 2, 2025, even more elaborate carbon structures embedded in the frozen droplets. The scientists revisited archived readings with cutting-edge tools and frameworks, drawing out nuances missed in early reviews. They pinpointed carbon-rich molecules with chained atoms, types tied to life's workings on our world, although abiotic pathways can yield them too. Such elements don't verify biology, yet they amplify evidence that Enceladus's watery depths might nurture it: fluid seas, warmth from orbital strain, carbon compounds, solid seabeds, places where chemical reactions can occur. These represent the key components scientists seek in their quest for potentially livable settings. What renders Enceladus particularly intriguing is this aspect. Its subsurface sea isn't cut off from the outside. It links straight to the cosmos via those geysers. Whatever substances are mixed into the seawater, be they compounds, microorganisms, should they be present, could get transported upward via fissures and expelled outward. Consequently, there's no requirement to set down on Enceladus, bore through kilometers of frozen crust, and descend equipment into a shadowy sea. Instead, spacecraft can simply traverse the geysers to gather specimens. Theoretically, signs of biology could be identified without any contact with the ground. NASA, along with various space organizations, have explored concepts for expeditions focused precisely on this approach. Probes crafted to circle Saturn conduct multiple sweeps across the geysers and examine the ejected matter using detectors vastly more precise than those aboard Cassini. Yet, there's a source of irritation in this scenario. Much like the challenges surrounding Mars sample retrieval, such endeavors get suggested, examined, engineered, and subsequently postponed. Factors like funding limitations, rivaling objectives, engineering hurdles, and changes in governance play a role. The soonest a specialized Enceladus probe could take off would be the middle to latter part of the 2030s. That's over 10 years in the future. In the interim, the clues keep building. Each fresh review of Cassini observations uncovers greater intricacy, stronger suggestions that Enceladus isn't merely suitable for life, but could genuinely harbor organisms. We possess a celestial body featuring a vast sea, sources of power, and organic compounds venting their mysteries right into the void for us to examine. Yet, we're holding back. Saturn boasts additional satellites harboring underground seas. Titan, that massive orb with its dense gaseous envelope and pools of methane, undoubtedly conceals a liquid water reservoir far under its frozen exterior. On Jupiter, the satellite Europa maintains a sea that could hold double the volume of all water on our planet. Ganymede and Callisto probably possess seas too. As it happens, our solar system proves far from arid. It's saturated, brimming with concealed bodies of water trapped under layers of frost. These seas have endured for billions of years, steady and protected from harmful rays, perhaps bustling with forms of existence beyond our current conception. Chapter 9. The Hunter Before Blood. The image that comes to mind when considering a leech is likely something distasteful, a shadowy, slug-resembling being latching onto flesh, drawing blood, and causing a cut that oozes excessively due to the blood-thinning agents in the creature's spit. Leeches function as parasites, life forms that persist by extracting resources from hosts. They feature pliable bodies, making them hard to admire, and they seldom appear in fossils since delicate tissues don't often endure. However, on October 2, 2025, scientists revealed a leech relic that upends prior assumptions about these beings. Dating back 430 million years, it shifts the beginnings of leeches 200 million years prior to the oldest known traces. This specimen hails from a deposit renowned for its remarkable preservation, recording not only the creature's silhouette, but also the arrangement of its torso divisions, the form of its skull, and even traces of its inner workings. The element that astonishes experts in ancient life isn't solely the antiquity. Rather, it's the insights this relic offers into the nature of leeches prior to their parasitic ways. This primordial leech didn't consume blood. It acted as a pursuer, a dynamic stalker equipped with mandibles and a physique adapted for navigating vast aquatic expanses. It inhabited marine realms, unlike the ponds or land habitats typical of contemporary leeches. In all respects, it differed profoundly from the leeches familiar to us now. Today's leeches fall under the category Hyodudonier, part of the broader film Annelida, the segmented worms. They share close kinship with soil dwellers and ocean polychaetes. Each exhibits a framework composed of successive rings, yet leeches shed the setae, discarded the firm setae that fellow annelids employ for grip. In their place, they developed adhesive discs positioned at both extremities of the form, and their robust, adaptable bodies enable them to creep across surfaces or propel through water with sinuous motions. Crucially, numerous leeches have developed unique oral structures designed to penetrate flesh and draw blood, demanding special biochemical tweaks, anticoagulant proteins, and stealthy traits to evade notice. All these features are concentrated in their saliva, transforming a basic nip into an intricate method of parasitism. Yet 430 million years ago, such developments were absent. This ancient leech specimen featured a distinct physique, elongated and sleek, optimized for swift movement over clinging. Its mandibles were keen-edged, though unsuited for skin puncture. Instead, they served to seize, secure, and shred tiny aquatic critters in the open water. It functioned as a true predator, an active swimmer in the seas that pursued fellow creatures. The scientists examining this relic, whose work appeared in a respected scientific publication, portrayed it as a glimpse into a vanished era when leeches weren't the loathed bloodsuckers, but rather genuine stalkers within oceanic habitats. This find prompts a fresh perspective on leech ancestry. The blood-sucking habit and parasitic way of life emerged subsequently. It wasn't their starting point. Across those countless years in between, certain predatory leech branches altered their approach. Maybe they first turned to scavenging carcasses or nibbling at injuries. Perhaps they began opportunistically sipping blood from living hosts in fleeting moments. Gradually, those casual opportunists evolved into dedicated parasites, honing their feeding tools, salivary secretions, and habits to match the full-time blood-dependent existence we recognize now. However, the preserved remains reveal that leeches originated from a wholly different mold, and it sparks an intriguing query. Do predatory leeches persist today? Hidden branches that skipped the shift to parasitism? The seas remain immense and largely uncharted. Our charts of Mars terrain outshine those of the abyssal depths. Fresh species surface regularly, odd annelids and peculiar soft-bodied oddities that defy known classifications. It's quite plausible that in some remote oceanic crevice, an unprobed gulf or ravine, leeches endure as hunters, mirroring their forebears from 430 million years back. This ancient find underscores that evolutionary paths aren't linear progressions toward greater sophistication or advancement. Rather, it's a sprawling network of branches, with offshoots veering off, testing new paths, some thriving while others fade away, every group tailoring itself to the surroundings and prospects at hand. Chapter 10. How Words Reshape Reality. There's a form of psychological control so understated and pervasive that the target remains unaware until their hold on truth begins to slip. It's called gaslighting. The phrase originates from a 1938 stage production, adapted into a movie, where a spouse deliberately distorts his partner's sense of reality, eroding her confidence in her senses, recollections, and mental stability. He subtly lowers the gas lamps in their house, then denies any alteration. He conceals items and accuses her of losing them. He challenges her memories until self-doubt consumes her. Though the story was invented, the tactic it illustrated strikes at the core of human vulnerability. On October 2, 2025, experts from McGill University and the University of Toronto released research that recasts gaslighting not merely as trickery, but as a distorted variant of learning tied to how our minds process contradictory data. The paper, featured in a leading neuroscience periodical, frames gaslighting as a malfunctioning associative learning mechanism in which ongoing contact with misleading details from a reliable figure can eclipse raw sensory input. As they outline, the human brain perpetually constructs an internal framework of existence, a cognitive blueprint that anticipates future events. This framework gets refined through. There are two primary channels of data that shape our understanding: the direct input from your senses and the insights gained from those around you, particularly individuals you hold in high regard. In everyday situations, these channels work in harmony. For instance, you spot a red apple and a trusted person confirms it's red. The details align, strengthening your mental framework. However, gaslighting introduces discord. You observe a red apple, yet someone reliable insists it's green. Suddenly, your mind faces a dilemma. It has to weigh which input to favor more. When the challenger is a key figure in your life, someone you've relied on before, with influence over your emotions or social standing, your brain might opt to believe them instead of your own vision. This isn't a conscious choice or intentional override. It's an instinctive tweak in the neural system your mind employs to interpret the environment. Scientists employed neuroimaging and controlled behavioral tests to examine this dynamic. They presented subjects with various visuals, followed by accomplices, collaborators, aligned with the researchers who offered misleading descriptions of the visuals. These accomplices were portrayed as knowledgeable authorities, lending weight to their claims. Through multiple rounds, the subjects grew uncertain about their initial impressions. Upon being quizzed on what they'd witnessed, they more frequently echoed the inaccurate details from the accomplices, overriding their actual sightings. Scans revealed heightened engagement in brain areas linked to resolving discrepancies and updating recollections, zones that fire up when the mind revises its archived data to integrate fresh inputs. Far from indicating foolishness or frailty, this reflects the brain's innate function, absorbing lessons from the group. As social creatures, humans thrive on collective wisdom and mutual reliance. If your community warns that a specific herb is toxic, you don't test it personally, you heed their advice, and it safeguards your well-being. Yet, this very adaptive trait, our communal knowledge network, can be turned against us. When a dominant figure repeatedly disputes your reality, your mind might elevate their narrative above your recollections. Self-doubt creeps in. You second-guess your senses. Confusion and disarray set in, making it seem like reality is slipping away. In essence, it is. An outsider's assertions are reshaping your personal worldview. The consequences run deep. Gaslighting transcends mere emotional harm. It's a targeted interference with cognitive functions, capitalizing on the brain's methods for acquiring and retaining knowledge. Experts stress that grasping this vulnerability is crucial for protection. Awareness of how authoritative denials can sway you allows for countermeasures. Maintain logs, jot down details, snap pictures, establish tangible references for your experiences that resist verbal overrides. Seek corroboration from diverse perspectives, cross-verifying your views with those beyond the toxic dynamic.